Hello everybody, it's Mr. Spinelli coming to you live Wednesday, March 18th, first day of e-learning during COVID-19. We're going to start off with some easy integration problems and ultimately work up to some U-sub. So first problem here, integrating a constant, you should know that it's simply the constant times x plus c. So what's happening here is that you know that the derivative of a linear function, in this case kx plus c, is simply k, the slope, the number in front of x. So anytime you see a constant, you can technically pull it out. So you've got k times the integral of dx. The integral of dx is just x, so you get kx plus c. So that's just another way to look at it. Remember, you can pull constants out. So our next example, we got k times x to the n. So this is just a generic formula. Again, I can pull the constant out, and then I've got x to the n dx. Now this technically has two answers, and I'm going to give you both of those answers. So in the case that n is not -1, we'll get kx to the n plus 1 all over n plus 1. Again, that's when n is not equal to -1. Or we'll get k times the natural log of x, and that is specifically when n equals -1. So if you have 1 over x, the integral is ln of the absolute value of x. And of course, I should carefully select all this stuff, shift it over, and not forget my friend plus c, some constant. So that is the integral. You need to remember that rule. That's kind of like your power rule. And then, of course, ln, natural log, is a different rule. So we got to get most of these to look like x to the n. So a simple rewrite on this problem gives me x to the 1/2 plus x to the 1/3. So I'm simply going to add 1 to each of those exponents and divide by the same exact number. So I've got x to the 3/2 over 3/2 plus x to the 4/3 over 4/3 plus my constant, which rewriting gives me 2/3 x to the 3/2 plus 3/4 x to the 4/3 plus c. So remember, when you're dividing by a fraction, you can just multiply by the reciprocal. Now the answer probably won't look like this if this is a multiple choice question. Will actually look more like the form that the question was posed in, using the actual radicals. So I've got to write the 3 for the cube root, and there's my answer. Alright, looking at the next one, this is very common. Whenever you've got addition or subtraction in the numerator, you're going to want to split this up. So I'm going to split this up into x times x to the 1/2, and I'm being showing all my steps here. X to the 1/2 over x squared. So I'm just rewriting everything in a power form that I'm familiar with. Now this is really x times x to the 1/2 over x squared. That first term is just going to be x to the -1/2. The next term will be x to the -3/2. Now, neither of those exponents is -1, so I apply my usual power rule, add 1 to the exponent, divide by the same number. So I should get 2x to the 1/2 minus 2x to the -1/2 plus my constant. Rewriting that, I get 2 times the square root of x minus 2 over the square root of x plus my constant. Now you may want to actually factor here, depending on what the answer looks like if this were a multiple choice question. So I could pull out a 2x to the -1/2, and then I get x minus 1, and then obviously still plus my constant. So that would be written as 2 over root x times x minus 1. Okay, so two different ways you might see this answer. Again, watch my factoring video if this step did not make sense. Take a look at the next one. Classic distribution. So it's very similar to the last one, which was dividing, but now we're just multiplying. So I'm going to distribute that 2x pesky little stuff. So I got 2x plus 2x to the negative first minus 2x to the negative second. So I'm simply adding the exponents together since I'm multiplying. So if I integrate that, I get x squared plus 2 times the natural log of x. So this is that one where x is to the negative first, so that's natural log. Plus 2 over x. When I add 1 to the negative 2, I get negative 1, and I have to also divide by a negative 1, so that's why I got this positive here. And then I've got plus my constant of integration. So again, as always, feel free to slow me down or speed me up if I'm not going quick enough, or skip if this stuff's too easy. Next one, 7 sine of x over 3. Alright, now when you see this, I want you in the future to be able to get to the answer right away. This is technically a U-sub problem. I would say U equals x over 3, in which case du equals 1/3 dx. So let's keep this very basic, pretend like we've never learned U-sub before. Essentially, whatever I said is U, I need its derivative to exist somewhere. Now, I see the dx here and in my original problem, but I don't see the 1/3. So in order to get the 1/3, I have to actually fabricate it. So I'm going to rewrite this problem. 7 sine of x over 3 dx. Now I want to add the 1/3 in there. In order to put the 1/3 to match my du, because now du 1/3 dx is right here. But I've changed my problem. I multiplied it by 1/3. I need to actually multiply it by 1. So I'm going to multiply by 3 over 3, which is cleverly 1. So I pull the 3 out just because it's a constant. I can put it in the front. So everything I've added in green did not change the original problem, but it allows me to see what I'm going to replace. So now I'm ready to replace. I've got 3 times 7 is 21. I'm just going to pull all that out. Integral sine of u du. So again, I pulled everything out that was a constant. I had to add the 1/3 by multiplying by 3 over 3. The 1/3 dx gets replaced with du. Now I can integrate sine of u with respect to u. It's simply negative cosine. So I get negative 21 cosine of u plus my constant of integration, which, replacing with what u was, is negative 21 cosine of x over 3 plus c. And that is my answer. There's a cool box. So, another way some people sometimes need to see this, I'm going to do it a way that's usually kind of unconventional. So I'm going to actually solve, I'm going to do this in pink just because most people don't do it this way. I'm going to write u equals x over 3 again. du equals 1/3 dx. I'm going to solve this for dx. So if I multiply both sides by 3, I've got 3 du equals dx. Now I'm going to replace everything in the original accordingly. So the 7 sticks around. It has nothing to do with x or u. X over 3 is u. dx is 3 times du. Now you can see, here's my 7 and the 3, which multiply to make the 21 that was out front up here. Okay, and then I've got 21 times the integral of sine of u du, and I'm in the same place I was to finish off the last problem. So sometimes it helps if you solve your differential, comparing du to dx, for dx. That might help some of you. Some of you might have confused, so don't pay attention to that again. So let's take a look at another one. So this is why I wanted you to be able to just see these and know the answer right away. So any trig function with some constant multiplied by x is technically a u-sub. So du would be k dx. So in order to get the k that I need, I have to actually multiply by k over k. So I'm going to put a 1 over k out front, k in the middle, and everything else I'm going to leave exactly as it appeared. So now you can see k dx is exactly my du, and then here's my u, and I'm ready to just replace. So I've got 1 over k integral cosine of u du. Integrate cosine, you get sine, so I get 1 over k sine. I'm going to replace the u already, kx plus c. So basically, anytime you see a constant in front of x on any kind of trig function where it's a basic integration, sine, cosine, secant of x, tangent of x, any of those 6 that you remember, you're going to end up dividing by whatever that constant is because of the U-substitution that results. Let's take a look at another one. 1 plus tangent squared of theta. Well, this one's kind of boring because you just need to remember how to rewrite this because you don't quite know how to integrate tangent squared because I don't know anything that has a derivative that's tangent squared. So then I have to rewrite this as secant squared theta d theta. And how do I remember that? Well, I actually don't waste brain space for that. I only remember that cosine squared x plus sine squared x equals 1. If I divide this whole equation by sine squared, let's do that. If I divide everything by sine squared of x, I end up with cosine squared over sine squared is cotangent squared x. And I'm frozen. Patience. There we go. Sine squared over sine squared is just 1. 1 over sine squared is cosecant squared. Well, that didn't help me. So instead, let's divide everything by cosine squared of x. Well, cosine squared divided by cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared of x. So that is what property I used. So all 3 of these equations in black, green, and red down here are excellent to remember. I don't bother remembering the ones in green and red though because I just quickly derive them in my head because I only consume my brain space with this one here. Okay? So, integrating secant squared, I have to think who has a derivative that is secant squared? Well, just so happens to be tangent of theta. So that one's kind of boring, but you gotta know your trig properties involving the Pythagorean identities. Moving on. Let's go back to pink. Pink is fun. Cotangent squared of x. Well, we just wrote what that is. We know that cotangent squared x plus 1 is equal to cosecant squared x. So a simple rewrite means that I've got the integral of cosecant squared of x minus 1. Now I have to remember who has a derivative that's cosecant squared. Well, cotangent has a negative derivative of cosecant squared, so I get a negative cotangent of x. Integral of negative 1 is just negative x, and then I add my c. I hope I added my c on the last one. I sure did. So this one was another Pythagorean identity, just rewritten in a way that we don't commonly see. Alright, now time for getting some fun ones. So I look at this, and I see that I've got something raised to a 1/2, and I go, well, I can't expand that, so maybe I need to set whatever's inside equal to u. So that's what I'm going to do. So u equals 1 plus the square root of x, and I'm actually going to write it as x to the 1/2 because that helps me write my derivative, which is 1 over 2 square root of x, which I'm actually going to write like this. Why? Well, because I know what's going on. So if I look at this, actually let's bust out the highlighter. 1 over the square root of x, well I've got that because I got a square root of x in the denominator, and I've got the differential dx. So all I need is a 2 on bottom. So since you guys are pretty good at this by now, here's my 2 on the bottom, but if I put a 2 on the bottom, I also need to put a 2 on the top, which means I'm putting a 2 out front. So I multiplied this original equation by 2 over 2. So what results? 2 the integral, oh but wait, my integrands, my limits of integration were from 0 to 1/2 in terms of x, so I need to figure out how that changes. So if I plug in 0 into my u equation, I get 1, and if I plug 1/2 into my limits of integration, who chose these numbers? There's a typo. I want to do 4. Keep things simple. There's no problem with 1/2. I just wanted to keep things simple for our first definite integral. So that upper limit's going to be 4. When I plug 4 in, square root of 4 is 2, plus 1 is 3. Okay, so I've got the integral from actually 1 to 3 in terms of u. Now, inside my integral, I've got u to the 1/2 du. So now I'm ready to integrate. I get 2 times integral of u to the 1/2 is 2/3 u to the 3/2, and I'm evaluating this from u equals 1 to 3. Alright, so now I've got to plug in 3, subtract what I get when I plug in 1 for u. So this is Fundamental Theorem of Calculus Part 1. So I've really got 4/3 times 3 to the 3/2 minus 1 to the 3/2, which is just minus 1. So I've got 4 times 3 to the 3/2 over 3 minus 4 over 3. So a little simplifying, 3 to the 3/2 over 3 is really just the square root of 3. So I've got 4 square roots of 3 minus 4/3. Who knows how that would be simplified, but at any rate, we've got our answer. Let's move on to the next one. So I've got the integral from 0 to 1/2 of this mess. So again, first thing I notice is that I've got something raised to what I would call an ugly power. So I'm going to set what's on the inside equal to u. And let's see where that gets us. So u equals 1 plus 9x to the 4th. Taking the derivative of that, I get 36x cubed dx. So now I got to ask myself, do I see this du anywhere? Well, obviously I've got, let's switch colors there, let's go back to red. Obviously I've got my dx. I do have x cubed, but it's along with 4 other x's. So let's rewrite this original a little bit. So I'm going to write it as the integral from 0 to 1/2. And instead of x to the 7th, I'm going to write it as x to the 4th times x to the 3rd, because that's the same thing. And then I'm going to keep everything else the same. Well, what am I missing? I've got my x to the 3rd, but I don't have a 36. So I'm going to throw a 36 in here, which means I also need to divide by 36. So now looking at this, there's my dx. Where's my x cubed? It's here. Where's my 36? It's here. I fabricated it by multiplying by a clever 1. And now I'm ready to rewrite. And let's see what happens now. So I've got 1/36. Oh yeah, I wanted to switch everything from from x's to u's. So I'm going to do u of 1/2. So 1/2 to the 4th times 9 plus 1 is equal to 25/16. I'll let you verify that math. 0 to the 4th times 9 plus 1 is just 1. So I'm really integrating from 1 to the 25/16 when I switch to u's. So now I've still got this x to the 4th, but then I've got u to the negative 3/2 du. So how on earth do I get rid of the x to the 4th? Well, I've got to look back at my original statement, and I've got to solve my u for x to the 4th. So if I do that, I've got x to the 4th equals u minus 1 over 9. So I'm going to replace that where I see my x to the 4th. So when I do that, I've got 1/36, the integral from 1 to 25 over 16 times u minus 1 over 9, u to the negative 3/2 du. And now this is very much like a problem we did earlier on. I'm going to distribute, and I'm actually going to pull the 9 out that's on bottom. So 36 times 9 gives me 324. So I got times the integral of 1 over 25/16 of u to the negative 1/2 minus u to the negative 3/2. So what am I doing here? All I'm doing is distributing this u to the negative 3/2 to each of these, the u and the minus 1. So when I do that, now I'm ready to integrate. When I integrate, I get, let's see, do I have enough room here? Probably not. So I get 1 over 324 times 2u to the 1/2 plus 2u to the negative 1/2. And I'm evaluating that from u equals 1 to 25 over 16. Now, I'm going to let you practice that. You should end up with a final result, so ... you connect the dots, of 1 over 3,240. So again, the key thing here was when we did our U-substitution, we had to, as usual, when there's a constant involved, multiply by a clever 1, which in this case was 36 over 36, but we still had x's left when we got down to this step. So in order to get rid of those x's, we had to go back to our u-sub and solve it for that x to the 4th to get everything in terms of u. Alright, moving on. Next one, integral of secant cubed times tangent. Okay, and we got a 3x on the inside, but what you need to think about is I've got 3 secants and 1 tangent. The matter is how many secants do I need to set it as my u? So I think through. I go, what's my derivative of tangent? Well, it's secant squared. Do I have a secant squared? Yeah, I've got secant squared times secant, but I'd have a leftover pesky secant if I said that u was tangent of 3x. Well, what if u is secant, or secant squared? Well, if u is secant squared, the derivative of that is 2 times secant tangent. That could be interesting. But I'm going to just try a basic sub. I'm going to see if just a standard secant works. So secant, but I got to keep my input to that trig function as 3x as it appears in the problem. So if I do that, don't forget chain rule, you'll get a 3 out front. So I get 3 secant of 3x, tangent of 3x, dx. And I have to ask myself, do I have everything there? Well, let me rewrite. So if I rewrite the original, it's negative pi over 9 for my lower limit, 0 for my upper limit. I can write this as secant of 3x squared times secant of 3x tangent of 3x. So what I'll notice, my secant tangent is right here. So there's du. So this is really just the integral of u squared. Now I've got to remember to make my subs for those limits of integration. So if I plug in 0, secant of 0 is 1. Secant of negative pi over 9. Well, it's really secant of 3 times negative pi over 9. So it's secant of negative pi thirds, which is 2 because cosine there is a half. Secant is the reciprocal of cosine. So I'm really integrating from 2 to 1. Notice that those numbers are in reverse order. And then I've got u squared du. But what am I missing? I can't forget that I needed a 3, which means I need a 1/3 out front. So I have 1/3 the integral of u squared from 2 to 1. So now it's integrating time. If I integrate, that 1/3 out front stays there, and I get u cubed over 3. Evaluate that from u equals 2 to 1. So I've really got u cubed over 9 evaluated from 2 to 1. Well, this is going to be 1/9. Plug in 1, I get 1. Plug in 2, I get 8. 1 minus 8 is -7, so I get -7 over 9. Hopefully you're pausing these videos and trying these problems without me. And if you've got questions, you'll leave those questions in the comments. Alright, now we got a messy one. But is it really that messy? Let's see. So the first thing we want to do is think about what u is going to be. Oftentimes u is what's in a square root or raised to a crazy power. So I'm going to give that a go. U equals 1 plus 3 sine squared of x. In which case the derivative of that, don't forget your chain rule, it's going to be 6 sine of x times cosine of x dx. Well, let's see what I've got already there. Sine x, cosine x, got that. But I need that 3 to be a 6. So if I want that 3 to be a 6, I can just multiply it by 2. But if I multiply by 2, I've also got to divide by 2 out front. So I'm really going to have 1/2. That wasn't a 2. I'm going to have 1/2 the integral, I'll figure out what that is, of du over u to the 1/2. Okay, but let's figure out what our limits of integration are going to be. So if I plug pi over 2 in for x into my equation for u, I say, what is sine of pi over 2? And then I square that result, multiply it by 3, and add 1. I should get 4. Then I'm going to plug 0 in. Well, sine of 0 is 0, so you're just going to get 1 plus 0 is 1. So my limits go from 1 to 4. So I'm really doing 1/2 the integral of u to the negative 1/2 from 1 to 4, integration with respect to u. So I carry that out. I get 1/2 times 2 u to the 1/2. Remember, I add 1 to the exponent, I get 1/2. Dividing by 1/2 is like multiplying by 2. And I evaluate from 1 to 4. So I'm going to plug 4 in first. Square root of 4 is 2. Notice that this 1/2 and the 2 will just cancel. So I've really just got square root of 4 minus the square root of 1 as my answer, which is 2 minus 1. My final answer is 1. It's always fun when the answer's so simple. Alright, next one. Wow, these are getting messy. But, as usual, u is often going to be something inside of square roots. Well, let's see what would happen if u is everything inside of that square root. X times the sine of the square root of x. Alright, patience, freezing. Square root of x. What would du be? Oh no, x appears in 2 places. Take the derivative of the first times the second, plus take the derivative of the second times the first. This looks messy. Probably not RU. Alright, so let's try just u being the sine of the square root of x. Let's see where that gets us. So I'm only making it be part of what's inside that square root on the bottom. So if u is the sine of the square root of x, then du is going to be cosine of the square root of x times the derivative of the square root of x, which is 1 over 2 root x. And then let's see what we got. Let's switch this color up. Let's go purple. Do I have cosine square root of x dx? I sure do. Do I have a root x? I sure do, because you need to remember a basic property. The square root of a times b is equal to the square root of a times the square root of b. So I can separate the square root of x and the square root of sine of root x inside that radical in the denominator. So doing that, I notice that all I need is a 2. Well, how do I get a 2? I put a 2 on the bottom, which means I got to multiply everything by 2. This is really 2 over 2. Now I'm going to change my limits of integration. So if I plug pi squared over 4 in, I'm really saying what is the sine of pi over 2? That's 1. If I plug pi squared over 36 into my u sub, I'm really saying what is sine of pi over 6? And that's 1/2. So I make my substitutions, everything in terms of u, going from 1/2 to 1, and then this is u to the negative 1/2 du. Very basic integration. We've seen this before. I get 2 times 2u to the 1/2 evaluated from u equals 1/2 to 1. So I've really got 4 times the square root of 1 minus the square root of 1/2. And if you simplify that, you just get 4 times 1 minus square root of 1/2. Or you might also see this as 4 minus 2 root 2. Alright, just a few more. Here's a very basic one that I hope you'll be comfortable with. This is a classic u sub. You'll set u equal to the exponent, so du will be k dx. This should look a lot like when we did the integral of cosine of kx. So I need the k there, so I'm really going to have to divide by k out front. And then I've got e to the u du. So this will be 1 over k e to the kx plus c. So this should be one that you simply memorize the rule for. Or you see it so many times that you know that's the answer. Alright, here's another very basic one. Oftentimes with e, whatever's in your exponential will be your u. So u equals cosine of x. du is negative sine of x. And there we go. So obviously I don't have the negative, so I need to multiply by a negative and divide by a negative, or multiply by two negatives, whatever way you want to think of it. So I've got negative integral of e to the u du. Well, that'll be negative e to the u plus c, which is just negative e to the cosine of x plus c. And I didn't mention it before, so I should probably say it now, but remember that whenever you have an indefinite integral, that is, there are no limits here, you should always just take the derivative of your answer to see if it's correct. So let's take the derivative of this. Well, the derivative of e to the something is just the same thing times the derivative of the exponent, which in this case is negative sine of x. Well, negative times a negative gives me a positive, so I've got sine of x times e to the cosine of x. And then obviously the derivative of a constant is simply 0. So that is exactly what I had as my integrand in the original problem. Remember that the integrand is what you are trying to integrate. Let's see if I can highlight it. Just that. So that is my integrand, which is exactly equal to the derivative of the answer I got. So you can always check your work. Alright, I think this is the second to last question. Good math, Mr. Spinelli. 18 minus 17 is 1, so you got one more problem after this. Alright, this is another very common one that you may or may not get used to seeing. So u is what's on the inside of the square root. Du is equal to negative 3x squared dx. So again, I know that I've got two x's outside of that radical, but I've actually got 6 more. So let's see what happens. A little rewrite. I need the negative 3, so I'm going to divide by negative 1/3 and multiply by 3 as well. Sorry. Yeah. So then x to the 8th, I'm going to write it as x cubed squared. I know that's silly, but that's really just x to the 6th. That's my leftovers. And then I'm going to put my negative 3x squared. Where did the negative 3 come from? Well, this negative 3 and the negative 1/3 cancel to just simplify to just make a positive 1. So that's my way of taking care of the negative 3. So then I've still got the square root of 2 minus x cubed, which will ultimately be u. So now I ask myself, what do I have? Well, do I have the negative 3x squared dx? There's my dx, there's my x squared, there's my negative 3. So there's a perfect sub for du. Is u going to be replaced? I picked the same color. Let's go to gray. There's my u, there's my u. So all I'm going to have left over is that x to the 6th, or x cubed squared. So rewriting this a little bit, I get negative 1/3 the integral of x to the 3rd squared times u to the 1/2 du. So how do I replace the x cubed squared? Well, I look back at my u. Solve that. I get x cubed equals 2 minus u. And then that is exactly what I will replace in here. So I get negative 1/3 the integral of 2 minus u squared times u to the 1/2 du. And now I've got to expand the 2 minus u to this 2 minus u being squared, and then I have to distribute the u to the 1/2. So this is negative 1/3 the integral of u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2. I'll let you verify that that is correct. And then I integrate. I get negative 1/3 times 2/7 u to the 7/2 minus multiply the 4 by 2/5, I get 8/5 u to the 5/2 plus 8/3 u to the 3/2, and then obviously plus c. I could distribute the negative 1/3 to the c, but it's just some other c then. Now, simplifying a little bit, maybe you want to factor out u to the 3/2, which is what I'm going to do. And I'm actually going to factor out the greatest common divisor, or sorry, the least common multiple of 7, 5, and 3, which conveniently are all co-prime to one another. They're all distinct prime numbers, in fact. So I'm going to have negative 2, and I'm going to factor out the 2 that's in the numerator, because 2 divides 8 and 8. So I got negative 2 over 315, and then I'm factoring out the smallest exponent, which is 3/2, and I end up with 15, and I'm going to replace my u's now. Why did I do that? I did some craziness. Woo! Mr. Spinelli, what are you thinking? Actually, let's not go crazy. Let's keep it simple, stupid. I wrote the answers simplified and then not simplified. So let's keep it simple. Negative 2 over 21. Replace u, it's 2 minus x cubed to the 7/2. So I'm just distributing the negative 1/3. Plus 8 over 15, 2 minus x cubed to the 5/2. Minus 8 over 9, 2 minus x cubed to the 3/2. Plus c. So if you're a nerd like me and you wanted to get the answer simplified even further, you can write it as negative 2 over 315, and this really isn't that much prettier, square root of 2 minus x cubed times 15x to the 6th plus 24x cubed plus 32 plus c. Much more likely to see this answer show up on a multiple choice if this were to be a multiple choice. But the key concept here is that the derivative of our u was an x squared. And we actually had 8 x's out front. Okay? Since we had 8, we had 6 leftover x's. Well, our u involved an x cubed. Well, the exponent 3 is a divisor of 6, which is how many x's we had left over. So that's a common situation where you'll end up replacing part of what remains in terms of x with your u sub. Last question, and this is just a fun hodgepodge of stuff. You notice that you have the same thing inside the sine function and inside of the square root function. So let's try setting that equal to u. So u equals 1 plus the natural log of 2x. Remember, the derivative of the natural log is just the derivative of the inside over the original. So that would be 2x over, sorry, the derivative is 2x. It's just 2 over 2x dx, which is really just 1 over x dx. Side problem for you. Show that the derivative with respect to x of the natural log of some constant times x to the n is simply n over x. There's your side project for homework. Back to our problem. Do I have the 1 over x dx? You bet your bottom dollar. There's my x in the denominator, and there's my dx. So this is a pretty easy substitution. I'm going to have the integral of the sine of u minus u to the 1/2. All of that integrated with respect to u, which integral of sine is negative cosine. Then I got minus 2/3 u to the 3/2 plus c. Rewriting that with u's plugged back in, I get negative cosine of 1 plus the natural log of 2x minus 2/3 the square root of 1 plus the natural log of 2x, that quantity cubed, still square rooted, plus c. And there's my final answer. Thank you for watching. I hope you are staying safe and sane. Have a wonderful rest of your Wednesday.